Hello everyone. In today's lab session, we will talk about two things that we have been discussing in the lecture slides unit 4. One thing is we'll see about the power, how power is represented. So again, we'll see the dotlet first, how power is represented inside the dotlet. We will look at the report power command, what numbers are reported, how they are reported. Then we will look at the clock gating, the power compiler clock gating. We'll implement a clock gating style. We'll see how the netlist looks like, what part of RTL helps you in what part of RTL does design compiler take into account before clock gating the logic. We'll see the clock gating cell types in the library and so on. So let's first open up a dotlet and see what is inside the dotlet that works for power. So this is the synopsis dotlet. Let's open the slow corner one. Now, easiest thing to search for power. So now see here, there's a leakage power unit which is 1 picowatt. There's a default leakage power derivative. Let's not worry about it. Anyway, 0. There's a default cell leakage power which we talked about, 0. Library features, report power calculation. All these three, report delay calculation, noise calculation, power calculation, they enable if they are set in the library. Any tool that reads this dotlet, like DC or PT, it will help you to find out how the power is calculated. We might see one example. This just enables when the user can see how the power or timing or noise is calculated. Right? Please note, there is no dynamic power unit. Dynamic power unit is always calculated from the units of voltage and current. Only leakage power unit is given, and both of them may be different. Right? Now let's go to similar to the delayed LUT templates, there is a power LUT template. So this LUT template is for the delay. For example, this LUT template VIO771. This is the delay. This is used for delay. There's power LUT template. So one of the templates tells us that it's a single dimensional table. The only variable represents the input transition time. So there is another LUT template, power output. So one is the power inputs one. So this must be used for input power. Power output. So power input will depend on the input transition time. Power output here, the table suggests that there are two variables: input transition and total output net capacitance. So this must be used for power, the output power. And now let's look at a cell. So this is the first cell we encounter, the AND2X1. So this is the cell leakage power here. This is a 90 nanometer library, so leakage power is not a big problem here. The leakage power unit is picowatt, so yeah, the leakage power is not used for a cell. But as the technology goes shrinking, the leakage power keeps on increasing. You can see that if you have an access to if you ever have access to the lower technology libraries like 45 nanometer or 22 nanometer or 20 nanometer, you can look at the power numbers. You can compare the power numbers across each cell. So you will see that as the technology shrinks because of the VT lowering, the leakage power increases. Now also note that the library does not contain the VT value, because the tools, the EDA tools, they are not concerned about the VT value. They are concerned about the effect of the VT value. So what VT value will do, for example, a reduced VT value will result into a higher leakage power. So that is represented in the power number itself. So the tool does not use the VT value. It uses the byproducts, that is the timing, the power, the area. Right? So this is the cell leakage power. So yeah, now see that it also has the state dependent leakage power. So it's an AND2 cell. So for all 4 states, this tells us even A1 0 and A2 1. This is both A1 A2 are 0, both A1 A2 are 1, and A1 is 1 and A2 is 0. These are 4 states, and for each of those the leakage power is different, which is expected because each of these 4 states there will be 2 NMOS, 2 PMOS, and plus there will be 1 NMOS inverter. So AND gate is built like an AND gate plus an inverter, and a 2-input NAND gate has 2 PMOS, 2 NMOS plus 1. So there are total 3 NMOS and 3 PMOS, right? 6 transistors in total, and depending on the state, some of them would be off or on, depending on each of these states. So the leakage power becomes different because the leakage current is different depending on all these cases. So we see that we notice that these 2 cases, when either both are on or both are off, so this case has the highest leakage power. When both are 0, A1 A2 are 0, it's 5.6 e to the power 4, and 10 to the power 4. Rest figures are even, sorry, this one looks more, right? 9.13 into 10 to the power 4. So each of these states has different power, and there is one there's one cell leakage power number also. I guess in this case the cell leakage power number is just a copy of the lowest power value, right? This is the lowest power value. No, not the lowest, not the lowest. This is the lowest. So in this case, the cell leakage power just matches one of the power numbers among all the 4 states. So, but when DC will use this leakage power number, since all the 4 states are represented, it will use the state dependent power. It will. I am not sure. It is most likely that the cell leakage power number, which is the default value, will not be used by DC. Right. So, however, if there is some other tool, is also free to leave this dotlet, and it might use it. So all the numbers are here. The default cell leakage power number is here. All the state dependent leakage power numbers are here. Now let's see. So there are, again I'll repeat. There are 3 types of. There are basically 2 types of power numbers. One is leakage power, the static power number. We saw how it is represented. Then there is a dynamic power number. The dynamic power is divided into 2 parts: the internal power and the switching power. What dotlet will contain will be the internal power, because dotlet contains the cell data, the standard cell data. Whatever power is consumed during switching, during the dynamic activity inside the cell, is the internal power. The switching power is calculated from the capacitance of the net of the wire, right? So that will come. That synthesis DC will use the clock frequency. So the formula is 1/2 CV square S. So DC will use the clock frequency, the switching activity, and it will calculate the switching power based on the net parasitic, right? So what we'll see in dotlet will be the static power and the dynamic power internal. So now we see here that pin A1 has a table called internal power. It uses the power inputs table. Index 1, as we saw, represents the pin transition. So it has 2 power. It has, again, it's state dependent. So A1, the power that is consumed by the gate when A1 switches, for the case when A2 is 0, the rise power so this case here is the internal power when A1 switches, when A1 rises and A2 is 0. This is when A1 falls. This is the case. Now the second table here is actually does not tell the when attribute, so it is the default attribute, the rise power and the fall power. Are the values same? Yes, the values are same. These values are same. And for a particular case, these values are also negative. If the DC finds the value is negative, it will take it as 0. Now let's look at A2. A2 will have a similar internal power table. When not of A1, the second table could have been when A1 is so this table represents when A1 is 0. This table could have represented the values when A1 is equal to 1. But so you will find that not all dot-lists are same in terms of the representation. It wholly depends on the team that is doing the characterization, what kind of characterization it does, what value it uses to put in, how many state dependent tables it is. So all of these state dependent data depends. I mean, the more data you want, the more granularity you want, the more simulations you have to run, the more machines it consumes, the machine time it consumes. So you need to have a lot of resources to do a complete accurate analysis. But many times the characterization guys will make some assumptions which are valid to reduce this machine time, to reduce the compute time. So and they will make some trade-off. So in some of the dot-lists you might find that there is no state dependent internal power, there is just one value. Again, cell leakage power, you might find that cells have just the default value. Now this default value should be the worst case of all the states that are possible, and so on. So not all dot-lists are same, not all characterizations are same. It depends on the team that is doing it and how many resources you have. So output will have the internal power. Now it has so output power related pin A1 means that whenever A1 transitions, so whenever there is a transition from A1 to Y, how much power does the cell consume as the output? Rise power, fall power, again related to A2. Rise power, fall power. So every cell in fact will have cell leakage power and internal power of inputs and internal power of outputs. So this is all about dot-lib. Now while we are on the dot-lib, let's also see the types of clock gating cells available for us. Now before that, let's first see the type of clock gating cell that is supported by a dot-lib. So let's look at this cell. Now this cell is, by description, it is rising edge latch based integrated cell. The keyword here is your latch posits. Right? So in dot-lib, a clock gating cell which has the attribute latch posits will have this kind of structure. What it means is that there will be a latch, of course. The clock gating without the latch is not a good method because it creates a lot of problems. The timing becomes much more complex. The latch makes sure that the enable at this point. The latch makes sure that enable at this point does not transition. Whenever, for example, for the AND gating, the enable here makes the latch makes sure that, so this latch works on negative edge. So this latch makes sure that enable does not toggle when clock is on. This is very important. If the latch was not there, you would have to do extra timing checks, extra checks to make sure that this generated clock here does not glitch, does not clip. So the latch provides that functionality to you, obviously at the cost of an increased area. But whenever you use clock gating in your cell, please make sure it has a latch. So the latch posit attribute here tells design compiler that this is the kind of structure that is represented by the cell. Obviously, there will be a function attribute which will define the function. We will see the dot-lib. So this rising edge means that it is used for flip-flops that are triggered by the rising edge clock. Latch is clear; it has a latch, and it's an integrated cell. That means in dot-lib, this is one cell with pins EN, CLK, and GCLK. Now it can have added functionality for DFT for a scan enable kind of pin. So whenever the scan enable pin is before the latch, it is called latch posits pre-control. The scan enable could be after the latch. So always the scan enable will be ORed with EN, which what it means is that, so whenever enable is 1, the clock, the G clock here will not be disabled. That means there will be a pre-running clock on GCLK. Whatever is on CLK will be passed on to GCLK whenever enable is 1. Now enable is a functional signal. It will depend on some functional conditions to be true, right? We'll see one example to make this point clear. But in scan mode, whenever we are doing DFT, we want that all the clocks should be pre-running. That means irrespective of the functional condition, it should always be 1. So this can enable, if the control comes from the top level, whenever we put the block in scan, we will make this 1, and since it's an odd signal, it will make sure that whatever is on clock appears on GPLC in the scan mode. So we do not want this clock to switch off during scan mode, because if, let's say, functional enable is not there, if the enable condition function is not enabled, we still want that in scan this GCLK should represent CLK. So that's why we give the control. If the control is before the latch, it is called pre-control. If the control is after the latch, it is called post-control. So the pre and post control where the OR operation takes place. Right? Now there will be a similar circuit for the flip flops which trigger on the negative edge. It is called latch negate. Again, it could have a pre-control and a post-control. In the positive edge trigger type logic, the gating is AND. In the negative edge kind of logic, the gating is OR type. The clock polarity is inverted. If the circuit here works on the triggers on the negative of the clock, the latch will work on POS. It will become transparent on the high pulse. In the case of POS logic, rising edge logic, the latch will become transparent on the clock low pulse. You can draw waveforms. We have already seen one waveform in the lecture slide. You can draw waveform and confirm that indeed this is the functionality that we want. Now let's see the dot level. Now what I'll do is I'll search for this keyword latch underscore. So when we see that the first cell it hits is CGLNPRX2. This is the cell, and the keyword tells us that it is latch negate pre-control. Right? Let's look at latch POS pre-control if it is there, or latch POS if it's there. So there is a latch POS and it's a latch POS pre-control. Let's see what all cells are there. Latch POS, CGLPPRX2, CGLPPRX8. So the drive is different. There is X2 drive, there is an X8 drive, and CGLPPSX. This is post control X16, post control X2, post control X4, post control X8. So the pre-control has 2 drives, the post control has 4 drives. I'm not sure why, but this is how it is in the library. So let's look at the one cell, and it will form the bits. You can look at any other cell, other clock gating cell, and understand this functionality once you understand it. Important thing: don't use this true. Why? Because this is a very special kind of cell. This is a clock gating integrated cell. Don't use means DC will never use it to infer any logic, which is what we want. This is a very special kind of cell. The functionality does not come from the RTL. This is an extra thing that DC adds to save power. Although the functionality remains same, the functionality does not change, but this circuit is extra. Is not present in the RTL. It is only present in the netlist if we choose to add it. And DC should not use this cell to infer any other logic, any other type of logic. That is why don't use the circuit. This is very important. Don't touch this, which is also good because it means that DC will not optimize it into something else based on a function. So once the DC will instantiate it, it will in subsequent compile procedure this will not get removed once it's inserted. Right. Rest of the things are same. The state table is a special case here. So the state table tells here what is the functionality. So whenever clock is high, for example, the clock EN, SE and ENL. ENL is an internal signal. So whenever clock is high, see this is the ENL is N, means there is no change. So this works only when clock is low. Whenever clock is low and either of EN and SE is high, so LH, HL, HH, that means at least one of it is high because it's an OR gate. So EN and SE will be odd, ENL will be high. Right? So by this, DC knows that it's an OR type. So the EN and SE is OR. Again, let's see the function attribute. So SE is there are few other attributes. SE is the clock gate test pin, which tells DC that this is for DFT, this is a test pin. There will be the EN pin, and it's a clock gate enable pin. So by these attributes, DC knows what to connect there, what signal to connect to EN, what signal to connect to SE. Then CLK is clock gate clock pin. Then ENL is nothing but the internal pin. Internal means that this pin is not visible outside. This is not a port of this pin. If you see the Verilog, ENL will not be present. ENL will not be hooked up when it's instantiated. It's an internal pin which is only useful to tell DC what is the representation of this pin, what is the functionality of this pin. Otherwise, the ENL will not come outside of this pin. So that's why internal node is ENL. Again, GCLK is the clock gate out pin. State function is what? It's clock into ENL. So ENL helps us in making this state function concise. So ENL, we've seen earlier, ENL is nothing but the latched, the output of the latch. Before the latch, the SE and EN are all together, and here the ENL is gated with clock. So let me go back to the figure. So we are looking at this kind of circuit where so this is the ENL pin. This is the ENL pin. So sorry, this is the ENL pin after the latch, sorry, and this is the GCLK is handling of ENL and CLK. So it perfectly matches with the Totlib description, right? So now when we use the command set clock gating style, we know that what cells we should use. So for positive edge triggered logic, we should use this cell. We should use this cell CGLPPRX2. For negative edge logic, we should use this cell, pre-control cell. Now we see that there are various drives available, which is a good thing. Why? Because a clock gating cell at one time can have a very large fan-out. Why? Consider a 16-bit shift register, which conforms to the functionality of the type where DC can add such a shift register with feedback logic, a perfect circuit for inserting clock gating cells. So DC will insert a clock gating, there will be one gate, but now this one gate will be driving all the clock pins of the 16 registers, all the clocks of the shift register. So the fan out would be 16. Now consider what if there are 32 registers in the shift register bank. Again the fan out will be 32. So it is very important for the library to provide you high drive clock gating cells. Low drive clock gating cells actually have no use. Why? Because there is, if you remember in clock gating style command, there is a bit width attribute. That means we want to insert clock gating cells only on register banks which are wider than a minimum width. The default value of that is 3. Probably you would want to do it 4 or 8 to save an area. You want to save power in area 4, so you don't want to go too low. If you go 2 or 3, then there will be a lot of clock gates inserted with less saving in power. So you have to choose a value which is either 4 or 8 or something like that, something which is not too low and not too high. What that would mean is that if you choose the value to be 8, each of your clock gate would be driving at least 8 fan out. So it is very important to have multiple drives and higher drives of clock gating cells. The lower drives are of no use. So whenever you have multiple drives available, choose the one that matches your minimum bit width. For example, if X8 is available, I would recommend choosing either X4 or beyond, not below X4. Right? So this was about the Totlib. Now let's go to design compiler and see some power numbers. So I'll be using one of the labs. I already have the DDC. I will load this DDC. where the clock gating is non-inverted, and I'll show you what are the power numbers, how do we report power, and so on. So the design is same. This is the design we are referring to. So this is the design that we saw in the lab sessions of Unit 3. The same design I'm using. I'm using this again with command file, but I've already written out DD3 to save on time. So I invoke DC shell. I'll read the DDC. First, I'll have to set the anything you have to do. You have to set the search path, main path, and target library. Now I'll do the DDC. So it loads all the link, and now what I'll do is it's already, the design is already synthesized. It's already linked. What I'll do is I'll just do a simple report power. You can also check whether the design has clock gating by issuing a command called report clock gating. So if you do some, it has to update some, but the design does not have any clock gating, so it shows the number of clock gating elements to be 0, number of gated registers to be 0, number of ungated registers to be 2 and 4. Now let's do a report power. Let's verbose. So it will do something called it will do update power, and it gives some warnings that it is another sequential cell output. So that's okay. That it's telling us unannotated means that it's telling us that there is no switching activity here. We haven't annotated any switching activity. So it will use default numbers. What numbers are those? You will see. It records the Y load model first, then it records the global operating voltage. The voltage value comes from the dotlet we have read. So we have read the slope on a dotlet. So voltage value comes from there. Now it tells us what are the units. Dynamic power units are derived from DC and D units. It's 1 microwatt. Leakage power unit is 1 picowatt. It directly comes from the dotlet. Now it tells us what is the cell internal power breakdown. Internal power is the dynamic power. It comes directly from the dotlet. So combination power is this much. Sequential power is this much. So see, the sequential power is much more than the combination power. It means that there are a lot of resistors in this. Let's do a report area. So yeah, although the non-combination area, which is the sequential area, is less than the combination area, but the sequential power still is much higher than the combination power, which is expected because the sequential power works on clock, and clock is the signal that has the highest toggle count, and therefore the sequential elements consume a lot of power. Right? Even when a sequential element is not switching, because of the clock switching, it's consuming power. So what I'll do is, so cell internal power is this much. This is the total of combination and sequential power. Other power might refer to any memory, any macros. There is no memory or macro in this design, so the other power is 0. Now it breaks down. So this is the cell internal power total. Now the next line is the net switching power. This is the switching power. Dynamic power switching. Again, it's a wire load. The net capacitance is not accurate. It's just an estimate, and that is why you have very less net switching power. This power might increase by a lot when this design goes through place and route. So probably in Unit 5, when we will have a place and routing design for the lab, we will do a report power on that and see if the net switching power is. I'll probably try to find out a design which is like a pre-layout and a post-layout both same design. and we'll try to see how the power increases after 4. So this is the total dynamic power, and this is the cell leakage power. Again, cell leakage power is just the sum of all the leakage power numbers of all the gates in the design. Right? So you can yourself calculate the leakage power by simply adding up the leakage power values of all the cells that are used in the design. This is how the power number is represented. Now a question, we did not read any leakage power is fine, doesn't depend on phase, but we did not annotate any switching activity. So what numbers it is taking. So but you can use this command set switching activity, and you can check these numbers. So it is again we talked about two values, the static probability and toggle rate. Again this you can apply switching activity on per port basis, per cell basis, per pin basis. You could it has lot of you can select a clock for a particular signal, you can define the period, so you can do a lot of things with switching activity, but this is obviously a tedious job. So first of all you need to put some switching activity numbers on all the inputs and associate a clock with it. From the inputs, DC will calculate the switching activity of all the internal units. Now, but still better is to get the VCD, get the phase from the VCD file, which comes from simulation. That is the best way to doing things of annotating switching activity. I don't have any such example where I have a simulation data and activity for a particular design, but you could do that in an assignment. What you could do is from your simulation. You might have an example design, or even you can take a small RTL, have some combination, some registers in it, take it to a test bench, generate a VCD, generate the fare from VCD, and annotate it in the design compiler and see how that affects the power number. Right? But what I have done here is, what I'll do is, I'll write out a cell by using this command, right? Say, I have already written out a cell. And by using minus propagated option, let's see this step. The command is again right there. You specify the output file name. You specify if you want to see the propagated value, just specify propagated. Now this will let us. This will tell us what values of what toggle counts are using. This is the default step. Now see this. Direction is backward, okay, generated from the design compiler. If it, I guess if it comes from a VCD file, it's forward. I'm not sure about this. Version and all time scale. So duration is default. It gives a duration of 1000 nanoseconds. Now these are the cell inputs. These are the design inputs. Now for each of the design inputs, it is assuming that the static probability is 0.5. That means that every input signal stays in state 1 for half of the time, state 0 for half of the time. Toggle count is 50. So toggle count is 2% of the complete simulation time. So this is the default. These are the default numbers. You can again change the default. Go back to DC cell again. And put that on default. So these are the three default. So static probability is 0.5, toggle rate is 0.1. Okay, toggle rate is 0.1. Power default toggle rate type is fast switch clock. We have discussed this in this lecture session. What this means. The toggle rate is 0.1. Now let's see this. So toggle rate of 0.1 means that for per unit time it toggles. Yeah, I'm not sure why toggle count is 50 here. Appears that the toggle count here is okay, right? The toggle count is 50% of the toggle rate by definition. So toggle rate, toggle count is double that of the toggle count is double of toggle rate. So it would have been 1% would have been 10 times and no 1% would have been, so default toggle rate is 0.1 and 0.1 into Yeah, so toggle count is half of the by definition is half of the default toggle rate. Toggle rate being 0.1, so toggle count is toggle rate being 0.1. The total number of the toggle count is toggle rate into the duration divided by 2. So this is the default. So every input has its default value. Let's see the clock, which is more interesting. Let's call clock. Yeah. So CLK, the toggle count is 1000. What it means is that the toggle rate is 200. I mean, it's 2. So 2000, 2 into 1000 divided by 2 is 1000. What it means is that the clock toggles twice per unit of time. And in one cycle time, in one period, the clock toggles twice, which is true, right? Clock goes high and low in one period. That is why the clock toggle count is same as the duration. The toggle rate being doubled, since the toggle count is the toggle rate into duration by 2. The toggle rate here is 2. 2 into 1000 divided by 2 is 1000. So clock has a very high toggle rate, obviously. All other signals have the default toggle rate of 0.1. Now these are primary inputs, right? These are primary inputs, and so see, even here the reset also has a toggle rate of 0.1, but you don't want that probably. If you want to work with default values, please make sure you some signals which will stay static or which will toggle once you set the appropriate. You can use set switching activity to set appropriate toggle rates. Now these are the values which you see in decimal are the internal nodes. These are internal nodes based on the toggle count values and the static probability values of the inputs. DC is able to calculate both of them for the internal nodes. So that is why these numbers now change for each of the internal nodes, right? So this is the calculation that DC does. So you can see here all internal nodes have some value, some toggle count, some T0 and T1 values. This is all that is contained in SAFE. When you convert from BCD to SAFE, the structure would remain same. Probably you will only have the values for static probability and toggle rate for inputs only, because the internal nodes DC will calculate from the input system. No need to do anything special for them, right? So this was about power. Obviously, if you are able to get a good SAIF, your estimates would be good from design compiler. So we'll see, this was all about power. We'll see the power numbers probably in this slide, some more power numbers and post layout data. Now let's look at how to insert the clock gating. What I will do is I will remove the design. I'll insert clock gating on a very simple design to show you the what kind of RTL structures get clock gating. Let's look at the what RTL I'll be targeting. So this is just one file. This is a barrel shifter. I have just downloaded this code. It has inputs CLK, load, R shift, left shift, shift num, inbuilt, in and out. Now the functionality is that if you give load, if load is asserted, out will simply get in. The output will simply get the value whatever is at the input. So the register bank will get loaded, right? So out is nothing but a bank of registers. I think it's 8-bit register. Out is 8-bit register. Out will simply out would be an output. Yes, out is an output. Yes. So the output is registered, and these registers will load the value of default if the load is enabled. If the load is not enabled, if the load is 0, if you want to right shift, based on the shift number, it will right shift the input. So if the shift number is 0, it will not shift. If the shift number is 1, it will shift by 1 bit. Left shift, right shift. Again, this is a similar functionality for left. Only the shift direction is different. So now consider a case where load is 0, so it will come to R shift, and either you are in R shift mode or L shift mode, one of these two modes, but shift number is 0. What it means is that if the shift number is 0 and you are not in the load mode, you get out. Out is simply getting the data out is simply feedback. The data is simply fed back into the register with no change. This is the condition that represents this fact. Shift num being 0, you are in R shift mode and not in the load mode. Again, not in the load mode. In the left shift mode, out gets the feedback value, right? So this is the kind of structure where DC will add clock gating because it sees a feedback. For some case, it will see that there is a feedback from the output of this register to the input, right? Now let's see what happens when we synthesize it. Now, first of all, what we should do is let's read this file. Read file minus shift over. So this is it tells us there are 8 flip-flops there, and so there are case statements which are fill and time input. So now I'll do a simple compile without the clock gating. Compile alpha. I'll take the options from here. And I'm not doing any clock gating, right? So I'm not bothered about constraints right now because I'm more concerned on the structure. So I haven't applied any block. There won't be any timing constraint here, so it will go on very quickly. But whenever you are doing synthesis, I do not recommend doing this. Please specify some timing constraint. This is because I'm just showing you simply the functionality of clock gating. I haven't applied any. So this is so let's note down the area figure about 300.7. And let's do we have the Verilog already written out? So yeah, so I've already written out the Verilog to save time. Let's open this Verilog. So there is a shifter, no clock gating. This first. So this is the shifter. These are the 8 registers 0 to 7, and the clock comes directly. No change in the clock. All the logic goes on data. The output simply comes out of Q, right? So these are the outputs that come out of Q. Data gets all the combination logic. Let's see data here. N77 gets all these data inputs get all the combination logic, and the clock goes directly, right? Very simple enough. Now let me enable clock gating. So what I'll do, I'll just do a gate clock. That's the only thing I can do. I'll do. I am not specifying any clock gating style for now. Let's see what default value does DC do. What does DC do by default, right? So we'll do this. Now we see that the area is a bit higher. It is 314.5. Earlier it was 300.7. So obviously adding clock gate will increase area. We also see that there is a message called performing clock gating on the design. So DC is telling you that it is doing some clock gating on the design shifter. What clock gating it did? Let's report clock gating. Let's do a report clock gating. So it is telling us that I use a very simple RTA to express the fact that we should. By looking at the simple RTA, we can know that what exactly DC is. In a big design, it's not always possible to look at to understand the concept very clearly. So it inserted one clock gating element. That means one integrated clock gating cell is inserted. Number of gated registers 8. So there are total 8 registers. All of them are gated. So total 100% of the registers are gated here. Total number of registers is 8. We can also do a minus gated, and it will tell us what it did actually. So it inserted a logic, a clock gate called clock gate outrage, and these are the gate registers, right? We look at the netlist. Let's also issue this command set clock gating style. Now, if I do set clock gating style, this is telling me that what are the default values it is using. It is using a sequential cell latch Minimum register bank size to be 3. Here in this case it is 8, so clock is gated. There's something called enhanced clock gating. I won't go into this, but minimum bank size is 6 for here. Or let's not worry about setup and hold time. We'll worry about it when we come to minute 5. It is clock gating circuitry is AND for positive edge, negative edge is OR, and again control signal is control point is scan enable, observation logic is false. There is no observation point again in CFD specific, but these are the default values. But now let's see the netlist. I've already written out a netlist called shift.2. Now see, what DC did is it added a clock gate called SNPS clock. So there's one more design now. There's an extra design now since we have. If we would have not given no auto ungroup, probably DC would have ungrouped this clock gate. So there's a clock gate which is added, and DC is now using integrated clock gating cell from the library. So even in the default condition, DC sees that your library contains integrated clock gating cell ICG, and it has a cell that conforms to the default case. What is the default case? Default case was it used AND gating with latch. It has a scan enable pin. So it found the exactly same logic in your library and it used that. So you can first try the default values, clock gating with default values. If it works for you, good enough. If it doesn't work for you, then you need to work with the set clock gating style. I'm not going to do set clock gating style command in this session, but you can try it if you want. But the result should be similar because your library contains the only thing you will play with probably is the register bank width. If you want to target the default, it was 3, which I think is good enough. People increase it, in fact, they don't decrease it. So you can increase it to either 4 or 8 based on what your design, what suits your design, what suits your area and power number. But the default clock gating without even playing with the set clock gating style command is good enough only if your library contains an integrated clock gating cell, right? Which every decent mature library should have. So how this latch is now inserted? Now this latch is inserted. Let's look at the SNPS. So this latch is inserted here. This is the design. Simply this latch is, so this design contains nothing but a latch. It simply contains one module hierarchy. But now this clock is an input. The CLK is an input here. EN clock is the output. Net 43 is the output. TE is tied to 0. So TE is here tied to SE. SE is tied to TE. Because there is no scan inserted here, so it won't do anything to TE. In case of scan insertion, this will go to the test mode. Whatever the scan test mode scan level, whatever controls from the top level will go to this port, TE port or SE here. Now the important thing here is that all the registers here, out 0 to out 7, the clock here now does not come directly, does not come from the port, but comes from the output of the clock gating cell. So let's go to the figure again. So now the clock is coming from, all the registers are getting clock from here, from GCL, right? Now, so this is the clock goes as input, EN goes as input, the GCLK is the output. So in one of the conditions, DC found that one of the conditions is such that the data will be fed back to itself in the register, right? And that enable condition DC used to generate the clock. So this is the EN. So whenever EN is 0, this net 43, which is the generated clock, the rated clock will be off. So it will save power, right? CLK here is the running clock. Now let's see the logic of EN. What is the enable? So enable is generated from some combination logic, some NAND. But what we know from RTL that enable will be generated when, so enable will be off when the clock will be off. So the clock should be off only when the data is being fed back to itself. We saw that the condition when data is being fed back to itself is represented by the case where load is 0, that means it is not loading any value. Shift num is 0, all the shift num bits the 3 bits value, all of them should be 0, plus it can be either in left shift mode or R shift mode. So if you look at this logic N68, we see that it is generated from two nets NAND N124 and N123. We see that N124 in fact is the inverted of load. So when load is 0, N124 would be 1. When N124 is 1 and N123 is 1, Y would be 0. It's a NAND gate, right? So if you go back and trace back N123, you would see that you would notice that N123 is generated from shift num, R shift and L shift, right? Again N122 here, it's a combination logic between N122. N122 is nothing but it is again generated from some two wires N80 and N79, and this is N80 shift num 2 and shift num 1, right? So you would see if we go back, draw it on paper, you would see that the RTL condition what we were talking about, that load being 0 and shift num being 0 and either the block is in L shift or R shift mode, the same condition DC utilizes to generate VM. So if the condition is true, for the case where feedback is enabled, DC will switch off this clock. So, and the dynamic power is saved. Can we see some power numbers here? What I'll do is I'll again remove all the design. I'll again read this file. What I'll do is I'll again do a compile quickly without the clock gating. So area is lesser obviously, smaller area, and I'll do a report power with the default values. Let's see what it does. So these are the power numbers. Let us move this. Just move these power numbers without clock gating. And what I will do is now I'll say wait clock. Area is not increased by much. I guess just one cell area, and I'll do a report power. Now internal power is 15.27. and here the internal power is 15.9. So the internal power is definitely reduced. Net switching power, now net switching power is slightly increased by because the number of nets will be more now because the clock gating is there. But we see that 19.2, the dynamic power has reduced. Now from 19.6, this is 19.6 without gating. This is 19.2 with gating. And please note this is a very small design. It's just 8 resistors, that's it, right? So when you expand it to a very big design, now I have seen in my experience, I have seen designs that are very big, which have like 600k instances or even a million instances, instance count. They have like 100k registers out of those. These such designs will have gating percentages of up to 80%, 80-90%. All the that means 80 to 90% of all registers are gated. Imagine the power saving there. This is why it is the most popular power saving technique. It is not right now. It is not even considered a special power saving technique. It is available as part of compilator. You do a minus gate block and it is done. Right? So it's not something very special that you have to do. There's not a lot of effort that goes into it. So it's by default it's enabled in all the flows that I'm seeing right now. In our industry, in all the companies, in most of the companies, this minus gate block is enabled by default. Right. So this remains the most popular bandwidth power saving technique. Right. So what you could do as an assignment again, pick up a design, a bigger design, with probably a few more resistors. And so again, see that we saw that in the earlier example, we saw that the sequential power was, in fact, let me do a verbose. The sequential power was very much, it is very significant when compared to combination power in the design. Why? Because sequential power, there is a lot of toggling involved on the clock, right? What we could do again is that I remove the line, I clean up, I read this. Yeah, so sequential power is very significant because sequential power depends on clock toggling. Clock toggles a lot, 2 times per period. So the sequential power becomes very much significant than the compared to the combination power. And the clock gating in fact addresses the sequential power. Let's do a report power minus this. So if we do not do any gating here, we see that okay, in this case the power numbers are below. Yeah, 29% and 52% in the clock gating case. Probably it's the sequential power will go low. The combination power. You can do this experiment as an assignment. What you can do is make up a design with a significant number of registers, give proper constraints, do compile ultra without gating, report the power numbers. Again, then do compile ultra with clock gating, then report the power numbers in verbose mode, so that you are able to see the difference in the dynamic power on the sequential side, right? On the internal power, you can see that. So that will help you in appreciating the power of power compiler clock gating, right? So that was all. And so we saw the how to report power. We saw the power compiler clock gating. We spent some time studying the dotlet, how the power number is represented there, what kind of clock gating cells are available. We inserted clock gating. We saw that in fact yes, even for a smaller design, the power number does get reduced, the dynamic power number. We saw the leakage power. We saw a default cell. What are the default switching activity that DC uses if we do not give any fast power. So that concludes Unit 4. There's one more lecture on Unit 4, but this is the only lab in Unit 4. So please spend some time in reporting power and experimenting with power numbers for better understanding. Thank you.